Hey, Math 82 folks. Next time we meet, we're going to be talking about a second method for solving ordinary differential equations. It is the method of integrating factors. What we're going to do in this video is explain what the process is, and when we get together in class, we're going to delve more into why it works and work on some examples. All right, we are going to be looking at first order differential equations, and this time it's important that the ODE be linear. When you have a linear ordinary differential equation, you can always write it in this general form. So something times y prime plus something times y equals something, where those somethings are each functions of the independent variable. Now, let's standardize how this is written. One way to do that is to rewrite these equations in normal form so that the form of the equation you write will always be unique once you write it in normal form. So what we're doing is we're going to divide this entire equation through by the function a of x. Of course, a of x should not be 0. Think about it. If it were, then we wouldn't have a y prime term and we wouldn't have an ordinary differential equation. So let's assume that a of x is not 0, in which case what we've got here is our new normalized function in front of p that is now b over a of x. So p of x is our former b of x over a of x, and our right-hand side q of x is our former c of x over a of x. And of course, a of x should not be 0, otherwise we are dividing by 0. Okay. Now, let's look at a brief example and how we should put that into normal form. So in this case, t squared is playing the role of a of x, and minus 2t is b of x, and 4t squared is our c of x. Putting this into normal form, we are going to be dividing by t squared. So we get a y prime of t minus 2 over t y of t equals 4t squared. So, of course, we need to be working in a domain where t is not going to be 0. Otherwise, we risk dividing through by 0. All right. Now, when we have a first order linear ordinary differential equation in normal form, and that's important to keep it in this form because otherwise our formulas are not going to make sense, what integrating factor can be used to turn the left-hand side into a total derivative? Now, when we talk in class, this is going to gel, but right now I'm just giving you the formulations. So what we're going to want to do is take this left-hand side, multiply it by something so that I can collapse the left-hand side into something else that will make the whole problem easier to solve. Okay, so let's suppose I have this function that I'm going to call mu of x, and I'm going to call that the integrating factor for this differential equation. I haven't yet told you exactly what that is. We're going to see what that is as we work through this. We want to multiply both sides of the differential equation by this function mu of x, which we have not yet determined. This process is going to show us how to determine this. One thing I'd like to point out is that this mu of x, we say it is an integrating factor. So the key there is that it's not necessarily unique. In other words, there may be more than one type of function that you can use to accomplish the same thing. Now, in an ideal world, what we're looking for is that this function mu of x, when you multiply it by your function p, which pre-multiplies your y, that thing is going to just be the derivative of our function mu. Now, why do we want that? Well, if that's the case, let's work through what actually happens. Let's take our mu of x times y prime from above, and we are going to add that to, now this mu prime is replacing our mu times p. So if I've got a function so that the function mu times my function p actually equals its first derivative, that is going to make everything collapse in a way that is particularly convenient for us. Why? Well, now what we have is a really useful total derivative. And what does that mean? That means that we've taken this left-hand side, and because of that special form, we can collapse that whole left-hand side into the total derivative of mu times y. And of course, we pull down from the right-hand side the same mu times q that we've been dragging along this whole time. Once we have this total derivative form, we are now in a position to simply integrate both sides. So let's integrate both sides. When you integrate the total derivative, guess what? You just end up with mu times y. And when you integrate the right-hand side, we're just generally allowing the right-hand side to be an integral. Now that right-hand side, mu times q, may or may not be easy to solve, but what this does give you is a general form for the solution, because what we're going to do is solve for our solution, y of x, by dividing through by mu. And what do you have here? You've got the entire closed form solution using this mystery function, this integrating factor. All right, so you should be asking, okay, but what is that mystery function? That would be great if we can find such a mu that makes everything work like that. Well, how do we find it? All right, how's that going to work? How do we find that integrating factor mu? It's very wrapped up in what we want mu to do for us. So we know that mu needs to satisfy this relationship that we talked about. We want its first derivative to equal itself times our function p. So we're going to solve for the function mu that satisfies this equation, but guess what? This equation is simply another first order ODE. This is a first order ODE, basically in its own right. In its own right. So guess what? We have a way of solving this, because this first order ODE is, drumroll please, separable. And we learned how to do that last time. So that's really quite useful. So this ODE is first order and separable. So we can use separation of variables. Use separation of variables to tell us what that mystery function mu that makes everything easy for us should be. Okay, let's practice. Let's solve this. So I'm going to solve for my mu. I'm going to let d mu dx equal mu times p. That's our requirement. Using separation of variables, I treat these like fractions. You remember we talked about that. So d mu over mu is p of x dx. And of course, I am now in a position to just throw integral signs around that and integrate away. So d mu over mu, that leaves us with a natural log of mu on the left-hand side, and on the right-hand side, well, we don't know what the integral of p of x dx is, but we know it's integral of something. And since in this case, we have no limits of integration, we have to make sure to add a constant of integration. Okay, Well, when you have a natural log, what do? You exponentiate. So we have the absolute value of mu becomes e to the integral of p of x dx plus that constant. And just like we did before, last time we talked about separation variables, we can pop off that absolute value, and we have a plus minus e to the constant times e to the integral of p of x dx. So as we saw in our last video, this thing here is just some constant. And in this case, we can actually scale it to 1 because this integrating function is not unique. So since mu of x is not unique, in this case, any constant will work. Now remember, why is that? Because we don't actually have an initial condition or boundary condition to impose here. We're just looking for a general family of solutions. And so choose one useful solution from that general family of solutions, and the one I want to choose has a 1 in front. So we're going to let e to the c just be 1. In other words, choose a c that makes that equal to 1. Okay, so what does that actually give us? That gives us the following. All first-order linear ODEs can be solved using the integrating factor method. So here are the steps. First, you write it in normal form. Here's your normal form. There's a coefficient of 1 in front of your y prime. So that next, we can identify what this function p is. And you can see that's why it's important, because the integrating factor is determined by taking e raised to the integral of that function p. That, in the end, gives us the general solution to our ODE, which is simply 1 over mu times the integral of mu times q dx. All right, so I recommend that you become familiar with the general idea behind the integrating factor method rather than memorize the formula. That'll become easier once we talk about this more in class. And you should realize that sometimes the integrals involved are going to be quite challenging to integrate, but at least we will always have a nice closed form solution for this. Okay, we'll see you all in class where we're going to practice this some more.